Welcome back to our AI Research Agent series. I am Aad Fataya, and today's episode is so exciting because we are going to build the brain of our AI agent. Think of what we are about to create as a vast digital library. But instead of just storing information, it can understand and relate ideas or connect ideas in ways that will amaze you. Now, in our last episode, we set up our environment and we learned all about archive data structure. In today's episode, we are going to transform that information into a knowledge base that will let our AI agent answer complex questions very easily and with remarkable accuracy. So, let's dive in and build something extraordinary together. Let me show you the fascinating system we are creating today. Imagine having a brilliant research assistant who can instantly access and understand thousands of research papers. That's exactly what we are building today. And here's how it works. First, we collect research paper from archive. Think of this as gathering knowledge from the world's brightest mind. Next, we process this information in a way our AI agent can understand. Then we organize this information in a sophisticated database. Finally, we provide instant access to exactly the information we need. Let me show you the technical architecture behind this system. This diagram reveals how each component works together to create our intelligent research assistant. Let's walk through each step of the process. We start with research papers, PDF containing text, equations, and diagram. While this format works for human, our AI needs something different. We break each paper into smaller, meaningful chunks. Think of it like creating a smart index that preserves relationships between ideas. And then we come to embedding. Here's where the magic happens. We convert each chunk into what we call embeddings. It's a mathematical fingerprint that captures the meaning of the text. When two ideas are similar, their mathematical pattern will be close, even if they use different words. And finally, the Pinecone database. Here we store these patterns in Pinecone, our specialized database. It acts like a brilliant librarian who can instantly find related ideas across thousands of papers. Each step in this process transforms our papers from a human-readable text into a format that lets our AI agent understand and connect ideas in a powerful ways. Now that we understand the architecture, let's build each component. Now that we understand the architecture, let's start by creating the first component, the PDF download system. We will create a function that will download research papers from archive and organize them locally. I will show you how to handle this download efficiently and manage any potential errors. Alright everyone, let's start with the fun part, by creating our first component. Just a quick recap of what we did in episode 2. We installed the requirements, and we said we created a requirement to text that's located in the same directory as this Jupyter notebook. And the first function we create was extracting data from archive into a pandas data frame and saving it as JSON file. And we test this function here and we get the result. This is the Jupyter notebook and this is requirement.txt. And then inside files here, we have the archive dataset JSON. Let's open it with editor. So this is what we have so far. Okay, we have a JSON object here. It's an array of objects. We have title, a summary, author, archive ID, URL, and PDF link. Now the first component we are going to create right now is to download this PDF research paper using this URL. All right, let's return to Jupyter Notebook and start. First, let's understand the essential libraries for our download system. Pandas, we need this for handling our data frame containing paper metadata. Request, this will manage our HTTP request to download PDF from archive. And OS, we will use this for file system operations like creating directories and managing paths. Then our PDF function takes two key parameters: a data frame containing paper information including PDF URLs, an optional download folder path defaulting to files. The function will process this paper one by one, saving each PDF and tracking its location. Then before we download any files, we need to prepare our environment. We check if our target directory exists. If not, we create it. The PDF file names list will track the path of each downloaded file, which is crucial for our later processing steps. Now, we enter the main download loop. We iterate through each row of our data frame. Each row contains metadata about a paper, including its PDF link in the PDF link column. And then here's where we handle the actual download. Request.get sends an HTTP GET request to the archive server. Raise for status, check if download was successful. If the status code is in 200, OK, it raises an exception that we will catch later. This robust error handling is crucial when working with external services like archive. Our file naming system is designed to extract the unique identifier from archive URL using split function. Append the .pdf extension, create a full path using os.path.join for cross-platform compatibility, and finally ensures each paper has a unique traceable file name. When saving the PDF, we open the file in write binary, essential for PDF. The with statement ensures proper file handling and cleanup. Response.content gives us the raw PDF data. Write saves it to our local file system. Our error handling system catches any network-related exception, logs the specific error for debugging, maintains data consistency by adding none for failed downloads, and it allows the process to continue with remaining papers. Finally, we enhance our data frame by adding a new PDF file name column containing file paths. And just a note here, failed downloads are marked as none. And at the end, we return the updated data frame for the next processing steps. This enhanced data frame will be crucial for our text extraction and chunking phase. Let's run the code cell. And we get no errors, which means our code is working successfully. To use the function, pass your data frame containing paper metadata. This function handles all downloading and organization, and it returns an enhanced data frame with a new file location information. Any download failure are cleanly handled and logged. Let's run the code cell now. As you can see, all the PDF are being downloaded now. Alright, and we have now 20 PDF downloaded, alright? Now if we go to files, we can see all the PDF have been downloaded now, alright? Let's check our data frame now. As we can see here, we have the title, the summary, author, archive ID, URL, and the PDF link, and the PDF file name column, which contains the file path to our PDF. With our papers downloaded, it's time for the fascinating part, which is processing the PDF into a format our AI agent can understand. We will split each PDF into a carefully sized chunks, while preserving the relationship between ideas. I will show you how we will do this using LangChain text processing capabilities. Now that we have our PDF downloaded, we will process them into a format our AI can understand effectively. First, let's import our key tools. These libraries are crucial for our text processing pipeline. PyPDF Loader handles the complex task of extracting text from PDF, and Recursive Character Text Splitter will intelligently break out text into manageable chunks. Next, let's examine our PDF processing function. This function does two critical tasks. It loads and extracts text from PDF using LangChain robust PDF handling, splits the text into optimal chunks for AI processing. The chunk size of 512 characters is carefully chosen because it's large enough to maintain context and meaning and small enough for efficient processing. Optimized for transformer model context window. Then our text splitting strategy is sophisticated. First, we load the entire PDF content. Then we create a recursive character text splitter with a primary chunk size of 512 characters and a 64 character overlap between chunks. This overlap is crucial because it prevents breaking important concepts across chunks. It maintains context between segments and ensures no information is lost at the chunk boundaries. Next, let's look at our data frame expansion function. This function transforms our document collection into an AI-ready format by processing each PDF into chunks, preserving document metadata, and creating traceable relationships between chunks. For each chunk, we create a sophisticated tracking system. Unique identifier combining paper ID and chunk number, links to previous and next chunks, preserved metadata from the original paper, and the actual chunk content. This structure allows us to maintain document relationships, enable context-aware processing, and facilitate accurate information retrieval. Our error handling ensures robust processing of varied PDF formats, graceful handling of corrupted files, continuous operation even if individual file fails, and clear error logging for debugging. The resulting expanded data frame provides each text chunk with its context, complete paper metadata, bidirectional chunk relationships, and original document reconstruction capability. This structured format is essential for accurate embedding generation, context-aware searching, maintaining document relationship, and enabling sophisticated AI analysis. Now let's transform our original data frame into our expanded chunk-based version. This single line triggers our entire text processing pipeline. Each PDF in our digital data frame is loaded. The text is extracted and split into chunks. Metadata and relationship are preserved. A new expanded data frame is created at the end. And finally, let's examine what happens when we display the expanded data frame. The expanded data frame, as you can see, shows a completely different structure, multiple rows for each original paper. Each row represents one text chunks, new column for chunk ID and relationship, and original metadata preserved for each chunk. Notice how the chunk column contains the actual text segment. A pre-chunk underscore ID and post-chunk underscore ID shows a connection between chunks. Each chunk maintains its connection to the source paper through the archive underscore ID. The original paper metadata, title, author, and etc. is duplicated for each chunk. This transformation is crucial for our next step, which is creating embedding for our knowledge base. This is where the magic happens. We will transform our text chunks into mathematical representation called embeddings. Think of it as creating DNA sequence for each piece of text. I will show you how to use OpenAI model to capture the deep meaning of your content. Now we are moving to a crucial part of our system, setting up embedding. First, let's configure our environment and API access. This code looks for our .env file containing API keys, loads these keys into our environment, and use override equal true to ensure we have the latest value. Let's run the code cell. Now we are going to set up our embedding system, which will convert our text chunks into numerical representation. Let's break this down step by step. First, we need the necessary imports. These libraries will handle environment variable, secure input, and OpenAI APIs respectively. Next, we set up our API key. This line does something clever. It first checks if we have an API key in our environment variables. If not, it securely prompts to enter one. We then initialize our OpenAI client. This creates our connection to OpenAI services. Let's test our embedding system with a simple example. Here we are using greeting in different languages. The embedding model will convert this text into a numerical format that captures its meaning. And finally, let's check the size of our embedding. Let's run the code cell. This tells us how many dimensions our embedding have, a crucial piece of information we will need when setting up our vector database. Think of embedding like coordinates in a high-dimensional space. Just like you can describe a point on a map with two numbers, latitude and longitude, our embedding describes the meaning of text using these dimensions. Similar meanings will be closer together in this space. Now we need a place to store all these embeddings. This is where Pinecone comes in. We will set up a Pinecone index that will let us search through thousands of documents embedding. Let me show you how to configure it for optimal performance. Alright, now that we have our embedding system ready, we need a place to store and search these embedding efficiently. This is where Pinecone comes in. It's our vector database that will make searching through thousands of document embeddings lightning fast. First, let's set up our Pinecone client. Similar to our OpenAI setup, we handle the API key securely and initialize our OpenAI client. Next, we configure our serverless specification. We are using AWS region for our serverless Pinecone instance. This configuration ensures good performance and cost effectiveness. Let's run the code cell now. Now comes the crucial part, creating our index. A few important points here. The dimension must match our embedding, 1536 for text embedding 3 small. We use cosine similarity for combining embedding, and for more information about cosine similarity, you can check my previous tutorial where I explained it in details. And finally, we check if the index exists first to avoid duplicates. Let's add some error checking and initialization. This ensures our index is fully ready before we start using it. Finally, we connect to our index and check its statistics. This will show us important information about our index, like how many vectors it contains. This Pinecone index will be our knowledge-based search engine. It can quickly find the most relevant chunks of text by comparing their embeddings. Think of it like a library catalog system that understands the meanings of our document, not just their keywords. Let's run the code cell now. And we get the result. Now it's time to bring everything together. We will upload our text embedding into Pinecone and create our searchable knowledge base. I will show you how to batch this process efficiently and verify that everything is working correctly. Let's examine our expanded data frame that we will be uploading to Pinecone. Using ilog5, we are looking at the first 5 rows to understand its structure. Let's run the code cell. Each row represents a chunk of text from our processed PDFs with careful structured metadata. The ID column shows our unique identifier. Notice how they are formatted as archive ID, chunk number like 9308101v1 #0, and then #1 and so on. We maintain consistent metadata across chunks. Title shows the paper title dynamic backtracking, for example. Summary, for example, preserves the paper abstract. Authors lists the author, in this case M.L. Ginsberg. Archive ID keeps the original paper identifier, and URL maintains the source URL. Most importantly, look at the relationship between chunks. Pre-chunks ID links to the previous chunks, and post-chunks ID links to the next chunks. For example, chunk number 1 links back to chunk #0 9308101v1 #0. and links forward to chunk number 2, 9308101v1-2. This structured format ensures we maintain context when searching through our knowledge base. When we upload this to Pinecone, these relationships will help us retrieve not just relevant chunks, but also their surrounding context. Let's upload our process document to Pinecone, transforming them into searchable embedding along the way. First, we set up our batch processing. We are processing 64 documents at a time. For each batch, we prepare 3 components. We extract the metadata, unique ID, and text chunks we want to embed. Now for the crucial step. We are using OpenAI API to convert our text chunks into numerical representation. Each chunk becomes a vector that captures its meaning. And finally, we upload everything to Pinecone. Let's run the code cell now. Now let's check our final statistic. Let's run this code cell. This shows us how many vectors we have successfully uploaded and confirms our knowledge base is ready for use. With this complete, we have built a sophisticated knowledge base that can store thousands of research paper segments, understand their semantic meaning, quickly find related information, and maintain crucial context and relationships. This will be the foundation for our AI agent ability to understand and answer complex research questions. And there you have it. We have built a powerful knowledge base that can understand and connect ideas across thousands of research papers. In the next episode, we will create the tools that let our AI agent query this knowledge base and generate insightful responses. Thanks for watching, and I'll see you in the next one.